Yeah. Now we are able to hear you. Welcome you, sir. Welcome you. So, without wasting much time, I would like to take this opportunity to introduce our second speaker of this third day of the FDP. Uh, as we know that Dr. Kala is very renowned personality in this field, and Dr. Kala received the B.Tech and M.Tech degree in Information Technology from the Indian Institute of Information Technology and Management, Gwalior, in 2010. He received his PhD degree in Cybernetics from the University of Reading, UK, in 2013. He is currently working as an assistant professor in the Indian Institute of Information Technology, Allahabad, India, in the Center for Intelligent Robotics. He is the author of 4 books and over 100 papers, and he has numerous funded projects from government agencies and industry to his name. He is an active reviewer of leading journals of the domain, and he is a recipient of the Early Career Research Grant from the Department of Science and Technology, Government of India. He is a recipient of the Best PhD Dissertation Award from the IIIT Intelligent Transportation System Society and a scholarship under the Commonwealth Scholarship and Fellowship Program from the UK government. Over to you, sir, and thank you for joining with us.
Okay, first of all, apologies for being late. The best IT institutes in India, as you would know, always end up into technical troubles. It's a very holy ritual, and therefore I hope it'll be a great session. So my talk is on what I specialize at, which is robot motion planning. However, to understand why is this problem even important, I'll have to, of course, tell you a story. This is a typical robot as you would purchase it from the market. It's a bit expensive, around 25 lakhs. And it's very similar to a robot that you would have seen your students or your colleagues make. It has a differential wheel drive system, so 2 wheels turn in the opposite direction that make it move. It also has a computer system inside. Instead of a Raspberry Pi, it's a better one. It has a Atmega motor controller. And of course, like all of you, we control it using a wireless system, which is right here. Robots often collide with things, so it's got 2 kinds of things for that. It's got these ultrasonic sensors which send something in front, and because we could only afford 2 of them over here, so it comes up with a bump sensor. So when I am over here and I kick the robot with my foot, I do not know why. The robot does not sue. If I do it with my own PhD students, they'll sue me up. So it's a tactile button that shuts off everything. And the most expensive part of it is, of course, that it has got in a laser over here. The laser shoots, comes back and gives you the distance, and it also rotates 360 degrees. 270 of them are useful. The other is it detects its own body, which is known as a black spot, and we delete that. So a very similar robot to what you would have seen, just a bit expensive. Now, if I really need to do anything with it, I need a capability that I say, hey, robot, go to the lab where my PhD student is sitting, and the robot should be able to do that. And that's visually the problem. So this is exactly where I am sitting right now and giving this beautiful lecture. This is what we call as the lobby area. So I could have shown you my place around, it's no less than a 5-star hotel, and we've got an amazing lobby outside with nice sofas. This is technically the classroom, but then we do a lot of fun activities here. It's not for regular classes, it's only for super specialization classes. This is the lab. So the robot should eventually be able to go right from here all the way up to here where my senior most PhD student sits. These are also more or less proper cabins. Now, the question is, the robot that I showed you, similar to the ones that you make, how do they get that capability in order to go from here all the way up to here completely autonomously? So we say that motion planning is just one of the problem in robotics, and I speak in approximately 15 minutes next on the other sub problems. And if you don't solve those sub problems, then you cannot get anything meaningful done from your robots. Like most of your student projects, they don't do anything meaningful. So the first problem is what is called as the problem of localization. And the problem of localization means that inside this map, the robot should always be able to find out where it is. So when we actually operate this robot, the graphics that it shows us is that on a computer screen in front of my system, like here, the red dot will actually show where the robot is at every point of time. And then I wonder why cannot it use the same technology for tracking where my students are at every point of time. So as a robot goes, this red line would go, this red dot would go, and that's exactly the simulation that we'll get. That's called as the problem of localization, or knowing where the robot is, the robot knowing where in the world it is, or the robot knowing where inside the map it is. Is it here? Is it here? Is it here? Or the red dot moving as the robot moves. That's called as the problem of localization. The second one is this beautiful picture that you see. It's called as the problem of mapping, or making in a map of the world. That's a problem of mapping. Thereafter, there are two ways by which I define my motion planning problem. The first way is that the robot is right here. The robot itself has not moved. It's right here. It needs to go here. So the problem of motion planning is to make this trajectory. And of course, you can see that it's only considering the static obstacles. So the problem of motion planning is, given a source and given a goal, I should be able to construct a collision-free trajectory for my own robot that connects the source to the goal, avoiding all static obstacles around. That's the agenda for today's talk. And I redefine this problem specifically because as I go along, what will happen is that one of my own PhD students would be trying to enter into my own cabin like this. It happens. And therefore, I not only need to avoid the static obstacles, I also need to avoid the dynamic obstacles. And the two terms are therefore avoiding static obstacles. We say deliberative motion planning. The output is a trajectory that connects the source to the goal. And reactive motion planning, you see somebody, you react to the person in order to avoid the person. Okay, voice is breaking. Let me just check. How's my network doing? Okay, I am on network. So I will slow down a bit. I think I might have some network issues. So the last thing that I talk about as a sub-problem is what is the problem of control. Ultimately, the robot will be moved by a left wheel, I can accelerate again, and a right wheel. Now, how do you control the speeds of both wheels? What linear speed and what angular speed do you give them? Given a trajectory, that's a problem of control, and I won't speak about it much because usually there are lots of people in FTPs talking about control. So let me touch briefly upon the localization or where you are and mapping, which is how to make this map problems. Now, I'll touch mapping first, and in mapping, I'll assume that you always know your position or the localization problem is solved. If you have an expensive camera like the one that I have, there will be an application saying, using this application, you can click panoramas. So you take your mobile phone, you walk around 360 degrees, and it stitches all the images to produce a paranomial view. We do exactly the same with this robot. Laser hits and gets back. It tells me distance from obstacle right ahead. It rotates 1 degree, 2 degree, 3 degree, 4 degree, 5 degree, 360 degree. It gives me an image of a map. My robot travels and it keeps on giving me obstacle map images. I keep on stitching them. Once I keep on stitching them, I know that I am iteratively making in exactly the same image. So given a position, I can just stitch images that make this map. The other problem is what is called as the problem of localization. Now, I assume most of you are sitting in front of a computer screen. So just look at the four corners of your monitor, laptop, whatever, and suppose I tell you what is the distance of your two eyes. It's stereo vision, they can measure distances. Suppose I tell you what's the distance between your left eye and each one of the four corners. I also tell you what is specifically the coordinates of the four corners, how mapping is known. When I create a map, I also say this is a laptop and these are the four corners of the laptop and this is their actual position as given by my laser. So you can have your own local GPS system. I assume people know how those GPS work. From 3 satellites, you know the distances and then you calculate your position. We do exactly the same thing. So robots can detect laptop screen corners. They can detect where is the tube light. They can detect the doors. They find out the distance from the door, many such doors, and that is your indoor GPS system, using which I always know my position. Now, Of course, I do take separate session. That's not what organizers asked me. And those only talk about localization and mapping. The funny thing is, when I was saying that keep on stitching images, I said that location is known, so you know exactly how to stitch. Or for mapping, I assume location. For location, I said the four corners of your computer screen. I know exactly where the four corners are in the real world. So for localization, I assume a knowledge of the map, perfect knowledge. So it's a chicken and egg problem. For mapping, I assume location. For location, I assume mapping. I neither know map nor I know location. So it's called as simultaneous localization and mapping problem. That's not what organizers asked me to speak. I speak to us separately for that. So I'll assume the robot will always know its location. I'll assume this map will always exist. And if I make a trajectory, I'll assume that how to control the two wheels so that the trajectory is perfectly traced, is perfectly known. With these three assumptions, I will go on the first part, which is, given this map, I should be able to construct in this kind of a trajectory. Now, traditionally, the one algorithm that everybody knows for finding a path from A to B is a graph search algorithm. So if it would have been a physical thing where we were physically meeting, I would have said, how do you find a path from A to B? Graph search algorithm, BFS, DFS, Dijkstra's. And that's exactly the first thing that comes in people's mind. It's a standard graph search algorithm. That's also how I got into this kind of problem. My MTech guy told me, Rahul, this is the problem. I said, yes, I know the answer. Graph search algorithm, Dijkstra's, BFS, uniform cost search, Floyd-Warshall. So let's do exactly the same thing. Let's fit in small grids throughout this map. And once you fill in small grids throughout this map, you say every grid is connected to the neighbors, perform a graph search. Now, there's one problem that in computing, whenever there are parameters, there's a problem because you have to set what this parameter is. And not always will that be intuitive. And believe me, this lecture that is being given on a Cisco WebEx, I sometimes also record and give it on YouTube. Every student is watching it as a different resolution. So at which resolution do you receive it? There is a setting and you set it as per what you can receive it. It's very hard to set. If your resolution is too high, you will get video problems. If your resolution is low, you won't like it. So setting the resolution is very difficult. Same with robots. If I set the resolution too high, the robot is thinking. The graph search will take a long time. I'll soon talk about why graph searches happen in 6 dimension, not in 2 dimension. It'll take an infinite time. If I set it too low, it won't be able to see small openings. Like there's a very small opening here. If the resolution is very high, you do not know whether a robot can go inside or not. So we need an algorithm which is independent of a resolution parameter. And therefore, what we say is that the vertices of a graph will be randomly distributed. So I had the entire map, and in the entire map, I took in random vertices like this. They are placed anywhere except for obstacles. And what's a graph? Vertices, edges, vertices problem solved, edges. So connect every vertex with all vertices at a radius of r. So if the straight line is collision prone, like the robot cannot make this travel, it collides with the obstacle, do not add that. If it can travel, add it as blue. So these are the vertices, random, and these blue ones are the edges. And once you've got the vertices and edges, you have got this kind of a graph, resolution free. The only parameter is the number of vertices, and you can iteratively improve the number of vertices. Try with smaller ones. You have more budget, increase the number of vertices. You have more time, increase the number of vertices. It's entirely as per your need. That's also what YouTube does. If you know that you are buffering a video, it's getting buffered very fast, it increases the resolution, the video quality reduces, the video stops to buffer fast, it reduces the resolution so as to have a real-time performance. So now I've got a parameter which I can control based on what I observe. The problem is, if I ask a robot that go to my PhD research scholar and it takes 3 seconds to think, 1, 2, 3, I'll lose my patience. I'll be like, what the hell? Why is this robot taking that much amount of time? Now, the roadmap computation has exactly the same problem. So many vertices to be added, so many collision checks to happen. Remember, this edge got added because a virtual ghost robot traveled this entire distance and said it's free, and that's a costly algorithm. So all the collision edge checks, very costly, and it's taking nice 3, 4, 5 seconds, and I hate that. Therefore, we do construct this completely offline, as in, the first time the robot comes over here, we open the package. Once we open the package, we do the self-test, which you do it with when you buy laptops, of course, check the specification. Then we take the robot on a round in the evening so as to make a map. Once it makes a map, we let the robot analyze that map and make this graph called as a probabilistic roadmap. And once it makes a probabilistic roadmap, it's completely offline. When you purchase the robot, it doesn't know what's the source and the goal. It's completely offline. Now, why the term probabilistic roadmap? So let's first talk about the word roadmap. If you have a smartphone like I have and you love traveling, you would have had an application called as Google Map, and then you enter, this is where I want to go, search, get me there. It does an excellent job. How does it do it? Google has satellite images. Using that, it analyzes the roads, the intersection. Using community, it annotates the special things on the roads. It converts it into a graph or a roadmap. When you go on search, it only does a small graph search. It doesn't keep on analyzing images at that point of time. So that's where the word roadmap comes from, same as the roadmap created by Google for outdoor satellite navigation. This is doing it indoors. It's completely offline. When the robot is purchased, there is no source or a goal, and it is only considering static obstacles. Can Google Map tell you how to avoid the vehicle in front? No. The satellite images that was used for that Google Map did not even capture that vehicle. It's not real time. The static obstacles do not change, the dynamic do change. So it's only for static obstacles. it doesn't consider source and goal, and it gives you a graph embedding on the entire map that you have. It's called as probabilistic, not because they were probabilities, it's because the vertices are randomly generated. So random probabilities are similar. That's why it's called as a probabilistic road map. Now what happens is, when I purchase this robot, this thing is done. Now I ask the robot that, hey, robot, go to my best PhD student. So now I give a source, now I give a goal. The first problem is to connect the source and the goal to a roadmap. So you see this green edges which connect the source and the goal to the roadmap. Believe me, when you do this Google Map thing, that's the first problem that comes in. You are in a garage, you set search, your garage is not in the satellite images, so Google has to guess where will you lead to in the road network graph, and that's exactly the thing. So you add the source and the goal temporarily. Your garage never becomes a part of Google Map. It's added temporarily as a guess by Google that this is the road that it will lead to. And then you do a normal search. Dijkstra's, A-star, uniform cost search, whichever is your favorite algorithm, Bellman-Ford. I won't care about complexity over here. The number of vertices are small. If you don't get a map, then you can make this more detailed. You can add more vertices. If you want a better path, you can increase the resolution, add more vertices, and redo that up. And this is what is in a nutshell, the probabilistic roadmap technique, where this graph is computed offline using only static obstacles. Remember, it cannot handle dynamic obstacles. And this path is what is generated online in a real-time manner. Now, for reasons that I'll tell you in the next session, in the next segment of today's talk, these spaces could be 6-dimensional, 48-dimensional, very high. And therefore, what really happens is that computation of this roadmap, number one, it takes a long time. And number two, it produces a very dense graph, which also takes a high amount of time. So it's all about maximum representation using minimum number of variables. So could I reduce my number of samples, still increase the quality? For those of you who are listening to this session and believe that each and every pixel is getting transmitted through your limited connection, no, that's not happening. Some representative pixels, which are the encoded video, is getting to your screens and it's getting decoded. If we start sending each and every pixel, you are gonna, this is already terabytes of a video, much more than that. While in reality, it's not even gigabytes if you would have recorded it. So can I get the maximum representation by minimum number of samples for this problem? There's just a roadmap for the graph that I showed you. This one is more dense because I was doing it overnight. So that's something that I will be working upon next. Now to tell you the most complicated part of today's talk. Okay, my voice is losing audibility. Okay, so now I'll be telling you the most complicated part of the entire session. When I take it in physical presence, I usually skip this part because people would come and beat me up. What did you start speaking? That's also the hardest topic that I take in a 45-hour course over here. So just be with me, things will cool down pretty easily, pretty soon. One assumption that I made so far was that my robot is a point. And I was saying whether the point is free, whether the point collides, whether the point can travel the entire edge. So I was saying my robot is a point. Now I will give it a shape. And when I give it a shape, this is what I showed as the map made by my lasers. So this is the exact map that you saw made by the lasers. And now I say my robot is a square. My robot is a square like my mobile phone. It is not a point, and therefore I drew squares like this whenever I had to tell what is the robot. I couldn't just draw points like previously. So if you go here, robots are point. A point moves from here to here, not a physical robot moves from here to here. Now it has shape, and therefore they are squares. And therefore what I do is I say that I will solve this problem for a robot which has a size, and therefore I will have a function, say collision detection function, that takes my encoded robot, that takes my state of the robot, that takes my configuration of the robot, that takes a virtual robot as it physically appears, and it gives you a 0 or 1 depending upon whether there is a collision or there is not a collision. So for this square robot, let us say the robot can only move on the X and the Y axis. So this robot can translate like this, and this robot can translate like this. What it cannot do is to translate in the third axis, which is coming out of the laptop or inside the monitor. What it cannot do is to rotate. As of now, it cannot rotate. It can only move here and here, and therefore the configuration at any point of time can be encoded by two variables, X and Y. Why not length and width? It's constant. It doesn't change. So in AI, those things don't come into configurations. So what is the minimum variables that I need to encode this, a X position and a Y position? And therefore I make a new space called as configuration space with two variables X and Y. If I put any dot over here, it will have a specific X-axis value and a Y-axis value. And what I'll do is to visualize this in my mind, I will look at this entire world map and I will visualize a physical robot at that X and at that Y. So the robot will always be a point here. It's the encoding. And if you need to visualize it in your head, close your eyes, look at the complete map, and place a virtual ghost robot at exactly that X and Y. Two things may happen. It may collide, it may not collide. If it collides, put a black dot. If it doesn't collide, put a white dot and color this space like as I've done it over here. So I'll just walk you through what you see. This position, which means this xy, if I move any lower on y or any lower on x, there will be collision. And therefore, from this point, any lower y, any lower x is saying collision. If I move any higher x or any higher y, it's not collision. If I move any higher x, any higher y, it's not collision. Similarly here, this is the tipping point. I move it any bit, even a millimeter micron over here, it has a collision. That's a tipping point. If I move it any micron here, it's a collision. If I move it here, it's not collision, it's white. Now, the only thing you need to consider is that the probabilistic roadmap is not made in this space or the workspace or the 3D space or the physical space or the space that my beautiful eyes see, all the physical space where the robots act and do everything, all the space shared by humans and robots and everything. So this is the real space. This is a hypothetical space that I created just to visualize the problem. And my search only happens here. This is where random vertices are placed. This is where the edges are connected. This is where the roadmap is made, and it's specific to the robot. If you get a larger robot, this will change. If you get a robot which has some different capabilities, this will change. Now, it wasn't visible here, but the size of the robot was small and the size of the lines is large, but then that space has actually been left. And the best example of it is there's a small opening here. So visualize this thing as that there was a wall all around here, but then some thieves came in, they made a small opening here, and therefore specific type of robots like our undergraduate students, especially girls, can go in here, but big fat people like me, they cannot go in here. I won't even fit in here. So when you do this for a larger robot, you see that there is no tipping point. So here and beyond is obstacle because of this obstacle. Here and beyond is is obstacle because of this. So it will appear as blocked, which means a fat guy like me will have to walk all the way here. If there would have been a thin girl with a much smaller rectangle, the girl would have been able to travel right here. So the configuration space does depend upon the type of robot and the size of the robot. And this is where everything happens. I'll quickly take in the last example. So this time my robot can also rotate like this. It can translate and it can rotate. So this thing can move like this here, and it can rotate like the arrow. So this is 0 degree, this is 90 degree. This is the direction of motion of the robot. Now, how many variables do I need? 3. X can change, robot moving here. Y can change, robot moving here. And angle can change, robot rotating. So here and here, X and Y are the same, but angle changed. So this is my physical space, but my configuration space has 3 axes, X, Y, and angle. And remember, the angle is not shown like this because angles are circular. So you have to say it's circular. 0 and 2 pi should look exactly same as it is. Angle 4 pi is valid. It comes after this. However, if I show the cyclicity as well, it becomes a 4-dimensional graph that cannot come on a presentation like this, and therefore cutting the angle axis, the x-axis, the y-axis, and the theta axis. At any point of time, what will I do is I'll place a virtual robot at that x, at that y, and at that orientation. I'll first close my eyes, visualize the physical space, visualize a ghost robot at the same x, then at the same y, then at the same theta, and if it collides, I'll mark it as black. If it doesn't, I'll mark it as white. How you visualize this thing over here is whatever we did, the tipping off point over here, anytime here it has a collision, anytime here it's not collision. You do it for 0 degrees, stack it up here as an image like this. Then do it for 90 degrees, stack it as an image like this, which is here. Then do it for 180 degree, which will be exactly same as 0 degree. Then do it for 3 pi by 2, which will be exactly same as pi by 2 because of the symmetry. Then do it at 2 pi, which will be same as 0, and just interpolate things up. Luckily, you don't need to do it because there are collision checking libraries which do this beautiful spacing thing. And this is for a manipulator. So this is the first arm of a manipulator. This is the second arm of the manipulator. A manipulator, as somebody would tell you in this FDP, is encoded by 2 angles. The angle of the first arm, which is here, and the angle of the second arm also, which is here. So this is your first angle, and this is your second angle. Now, this is the first angle, and this is what is the second angle. Now, again, these are circular things in nature. How you actually visualize it up by taking in a piece of paper, and you say that in this piece of paper, the first axis is circular. So you make it circular by rotating it like this, and then you say, so it's a circular axis. The moment I turn a paper, it becomes a circular axis. There's no discontinuity. And you say the second axis is also circular. So you fold it up like this. It becomes a torus for the Englishman of you and a vara for the Hindi man of you or the Indian man of you. So that's the first axis, that's the second axis. So again, for this point over here, you will visualize the first angle, the second angle, see if it collides or not. And if it collides, put it black, otherwise put it white. That's the configuration space. Now you'll see the obstacles in the workspace and the obstacles in the configuration space don't look exactly the same. So they look absolutely different. So that's the first obstacle. Remember, it's circular. So it's this little thing. The actual one is circular. So this is over here, and this is over here. That's one of the arms over here. And this is the rock solid obstacle that you see around over here. They may not physically look the same because it's a very different space. And I do a probabilistic roadmap over here. And my last part of impossible things to understand is, okay, let me summarize the first impossible thing to understand. I'll just take 5 minutes of jargons and then I'll do normal lecturing. So if you want to construct the configuration space, first problem, identify what is the degrees of freedom of the robot. XY, XY theta, theta 1, theta 2, how many degrees of freedom does it have? Then, second, make a new image where every axis is 1 degree of freedom. So, the first space, which is the ambient space, I'm not calling as a workspace because manipulator people would have defined it differently. So, now make a new space where every axis is 1 of the degrees of freedom of the robot. Third subproblem, for every point over here, visualize the robot and see it collides black, it doesn't collide wide. And that's why I said that humanoids have 48 degrees of freedom, manipulators have 6 to 10, sometimes 12. The simpler humanoids could have 12 to 24. That's a dimensionality over which my probabilistic roadmap, it works. And that is what I should be able to solve for. So it's a 48-dimensional space for humanoids. The second thing that you need to know is that making this beautiful 48-dimensional picture is impossible. I would have better done a grid search. And hence, I only check whether things are black and white if it's a vertex or if it comes on an edge. I never make this picture, because making this picture is too computationally expensive. And because it's too computationally expensive, I do not do it. So with this, we come to the second part. And remember that probabilistic roadmaps are independent of the source and goal. It's done when you buy the robot. So with this, I come back to the fact that can I have a better encoding? This is terrible. Now, each and every sample, all that it does is that it tries to say that the robot will come here, make a turn over here. The robot will come here, make a turn over here. So every sample over here, it encodes the robot making in a turn. Other way, what's the shortest distance between any source and any goal? Straight line. If it touches if there's an obstacle and straight line is collision prone, what's the shortest distance? Tangent. Everybody knows geometry, tangents in a 48-dimensional space. How do I get tangents? So if I can model only the tangents, I get my shortest paths. I only need to model the tangents. The tangents are always next to obstacles. Popular question, if I know that tangents are the shortest distance, why don't I just compute the tangent using geometry? It's a 48-dimensional space known by an unknown function. How do you calculate tangents of a 48-dimensional space when you have a discrete algorithm in which the space is represented? You cannot calculate that up. And therefore, I place everything up near the obstacle so as to model all tangents. This tangent model, this tangent model, this tangent model, all tangents get modeled in a 48-dimensional space, remember. Or let's say in a 6-dimensional space, because probabilistic roadmaps fail in 48 dimensions. They go up to 6 to 12. And that's called as obstacle-based sampling. Here you generate samples inside obstacle and travel in a random direction. And when you get outside the obstacle, then you just stop and say, this is it. That's my sample. And hence, now it's only representing tangents, and therefore it is a better encoding. I don't need samples in the free space. They were useless. Delete them. So I'm representing the complete space using a significantly smaller number of samples. This does exactly the same thing again. So instead of stopping right at the boundary, if you stop right at the boundary, it's problematic. Making connection right at the boundary is difficult. So you stop at a little distance, little away from the boundary, little away from the boundary, not kissing the boundary, little away from the boundary, where how much away from the boundary? It is by a Gaussian distribution. So there will be some samples like this and this, which will be very far away from the boundary, most of them near the boundary. Now, modeling tangents is good, but it's also important to model departure from one obstacle towards the other. So how do I model for departure from one obstacle to the other? There's a neighborhood constraint. So this doesn't model all such departures, this does. And therefore, the Gaussian sampler, it generates most of the samples near the obstacle boundary because it is modeling tangents, y-tangents, shortest distance. And it also has some samples which are far away so as to have enhanced connectivity. So it enables me leave one obstacle and go towards the other one. Now, it turns out with both these techniques, this is a famous problem called as a narrow corridor problem. And to understand what's a narrow corridor problem in whichever city you are, when driving, you would have faced this condition that the roads are heavily jam-packed, occupied, there's a little space, and you're thinking, can I just go into that space? You say yes. Your wife next to you says, no, don't be crazy. And driving through it will be very difficult. And then you go around and you're fitting it up a little bit, trying to see, can you get through? 75% you are correct. You tell your wife, I'm the best driver in the world. 25% you cause a complete chaos. People are swearing at you, who the hell this guy is. With robots, luckily, everything is in the mind accurately made. So this problem is not there. But for any robot, for any technique, driving through a narrow region is very difficult. If you are packing up grids saying A-star algorithm grid search, your resolution of the grid needs to be very, very high, 1 mm. Because the robot has only 2 mm of space around, 1 mm here, 1 mm here. So your resolution has to be very high, 1 grid in 1 mm. And with the probabilistic roadmap, what happens is that uniform sampling, most of the samples are in the free space. The probability of generating a sample here is very narrow. A millimeter here, it's obstacle. A millimeter here, it's obstacle. It's very difficult to generate samples and tell the robot you can go through. So there's a famous bit sampling. It only samples narrow corridors. It generates samples inside the obstacles, travels in a random direction, gets free space. Obstacle-prone sampler would have added sample here. It continues to travel. So if it goes in its traveling from obstacle to free space to obstacle, then it adds samples in the between. And remember, adding these samples by any sampling technique is so difficult that obstacle-based sampler would have generated hundreds and thousands of samples to add one sample here, and that hundreds and thousands of samples would have just wasted my time like anything. So that's what is the bridge test sampling. Sometimes the spaces are so complicated, we have just one thing in mind: reduce the number of samples as much as possible. The 48 or the 24-dimensional space is impossible to model. It will generate millions and billions of samples, and I cannot do a real-time search using millions and billions of samples. So we generate samples as far away as possible, and there is intuitive proof why as far away as possible. If I tell you to model the space by drawing in a graph, 90% of you will draw what is called as a deformation retract, or the Voronoi diagram, which is just a line drawing that covers around the obstacle by larger space. So the smallest graph that can actually model the space is what is a deformation retract, which is just this graph. It covers all the connectivity. And therefore, we say if we want to model it up, we have samples which are as far away as possible. Why cannot I take a Voronoi algorithm freely available in the web and use the same? That would have been the best. They only work for 2 dimensions. They don't work for 24 dimensions, 48 dimensions. The same thing is what's done by the medial axis, as far away as possible. So maximum clearance, it just generates random samples and selects the one which have the maximum clearance. Medial axis generates samples inside obstacles, keeps traveling, keeps traveling, keeps traveling, keeps traveling, keeps traveling, keeps traveling. And then it generates a sample right in the middle of these, which is over here. And that's our favorite grid search. This is how the A-star algorithm works, except for now, instead of just packing it up as grid and connecting all of them to its neighbors, what I do is I generate random samples inside. if I get the connectivity good, otherwise I can always add in samples inside the grid. So that's going intermediate between a classical grid search and a probabilistic roadmap. And because it's going intermediate between the two, what I do get is that I get the completeness and optimality properties of the classical grid search, but then I'm not bugged up by a specific resolution. If I want, I can add resolution in runtime. So now what I'll go is Hybrid is doing all of them, and the RRT, or the rapidly growing random tree. So what happens in the probabilistic roadmap? The story that I told you was the classic story. You get a robot, you make a map, and then overnight it makes a probabilistic roadmap. That's not what happens now. Now you have manipulators, humanoids that operate in kitchens. Kitchens, even the static map, it changes every day. So when you cook, you leave a utensil as it is. Now, for a manipulator that is sharing the same space, that thing is a new obstacle. And because it's a new obstacle, the probabilistic roadmap needs to be made again. It's a 48 degree of freedom robot. So just because you left one utensil and your probabilistic roadmap cannot handle dynamic obstacles, now it has to recompute that. So it becomes expensive. So what we do is a parallel methodology that you fix in a source, you fix in a goal, you don't construct an offline roadmap. What's the point? The humanoid working at your home is changing every day. Items are moving here and there. So when the map is not static, what's the point in making a roadmap? So what you do is you just give a source and a goal, and then the robot starts to think live. And once it starts to think live, this is where it needs to travel, make a plan. Now, why a tree? Why not a graph? It's exactly the same as a probabilistic roadmap, except for it's curtailed from source towards goal. When the source is fixed, the shortest path needs to be computed from the source, so there's no point in adding cycles. For both the nodes that incur a trial cycle, you can find out which one is the useless edge and which one gives you the shortest path from the source. So a tree, and all that you do is you keep on growing a tree directed towards the goal. So you'll see more edges facing towards the goal rather than completely random. This faces the goal, this faces the goal, this also faces the goal, this also faces the goal. This goes out, oh, it's okay, but then this again faces the goal. This also is a little bit projected towards the goal. This is also a little bit projected towards the goal. You find very less edges which are going outside. So I grow a tree from here and I let it grow in all directions, but a little bit more biased towards the goal. And whenever a node hits the goal, I have my path. So it's still offline. It takes 2 or 3 seconds, but it's for cases where I cannot make an offline roadmap because the static map is changing. What advantage did it have to probabilistic roadmap? I knew the source, I knew the goal, so I could be directed towards the goal. Probabilistic roadmap construct a roadmap of the entire universe. This is strictly directed towards the goal from the source. And I can make it even more goal biased. So this is highly goal biased, you see. So this mostly is towards the goal. And I can search both ways. That's just for people who have learned AI well. They know that searching both ways has an advantage to just searching one way. So this is like our old story was Romeo searching for the Juliet, trying in all directions. This one is Romeo searching for the Juliet and the Juliet also searching for the Romeo. Just because then they meet at a ground which has technically a larger coverage, and finding out a path becomes a little bit easier. If you want a library that does whatever I talked about, of course, I'm not asking you to code anything. Of course not. Gone are the days when you will program deep learning neural network. So if you understand what I was talking about, and you are too cautious that I cannot program it up, honestly, even I cannot, The library is open source, available with a lot of documentation, with a lot of help, with a lot of tutorials. The only problem is, like every famous library, it's on Linux only, possibly Ubuntu. So it's called as an open motion planning library. And if you have used robot simulators and they come up with planning like the VREP or the ROS, they all use the open motion planning library. It takes care of everything. You don't need to do anything. You just load in scenarios like this and click on plan, and it'll plan. And if you want to write in papers, all codes are open source. Just change any code. It comes with its own utilities that also make in the graph for you. You don't even need to make a graph for publication. Change any part of the code, my code, and say test and make graphs, and just put those graphs as it is in the paper and publish the paper with whatever changes you have made. It is a very simple library. That's the Open Motion Planning Library. If you want to go a little bit more advanced, there's a library called as Move It. That one is a bit difficult. So it's a wrapper around the Open Motion Planning Library, and it's a default standard. They're growing every day as we speak. So if you are into motion planning and you haven't tried Open Motion Planning Library, I do recommend that is the first thing you should be doing. Now we talk about the other planning problem. So remember that I started by saying that the robot will make immediately after purchase a roadmap offline. Source and goal will be added, and then we will be computing a trajectory live based on that roadmap. But then making a trajectory takes in still a second. So then we said that we'll make a rapidly exploring random tree, which will grow a tree online, which will grow a tree, but still it takes in a couple of seconds. Now imagine you said everything that I did, you did everything that I just said, and you made a deliberative plan, and you're following it up, and suddenly what happens is that one of my research scholars who needs to submit his stipend form right now is getting late. So it's like this Bollywood movie where my research scholar is running with a stipend form in its hand and marching in towards my cabin. This research scholar is so stubborn, he won't see anything. He lose money, so he's coming in, and the robot has already planned a part. So the robot says that, okay, something is changing. Let me plan a new path in 2 seconds. But by the 2 seconds the robot plans a path, my research scholar is changed its position. The other example is sometimes what happens is that the robots are traveling, they plan the path, they're happy with it, they are driving around, and suddenly they see something dropping up from heaven right in front of them. So that was just the PhD supervisor who said, your thesis is terrible. I throw it away, and it comes right in front of the robot. Now, again, it cannot take in 2 seconds because the first thing it needs to do is to break in immediately. If it tries to make a new plan in 2 seconds, the thesis would be ruined by the robot, and thesis being ruined by the robot is a bad idea. So that's a human skill that we call as reactivity. You react to a situation. So if somebody comes running at you, if it's a girl, you go running. If it's a boy, you step aside. Reactivity. Humans react. So that's not what I will be doing in that. I'll be making my algorithm react to situations so that they can handle moving obstacles, dynamic obstacles, obstacles that suddenly come, my running research scholars, and so on and so forth. So now I'll be programming in for those types of behaviors. Without wasting much time, I'm a bit short, so I'll go straight to the actual algorithm. So assume this is the same map. Why do you see larger obstacles? Because I only drew a smaller map, which was just around the robot. And this is what I say is the robot. So that's the robot. This is the map. And these are 1, 3, 4. 1 and 3 are moving people. And 2 and 4 are static obstacles. So this is a table that is kept over here. The robot wants to move here. And this is a array of flower pots over here. And these are 2 moving people. So what you imagine is the robot is negatively charged. So there are negative electrons which are all around this robot. And the goal is highly positively charged. So there's a very big positive charge that's on the robot here. So of course, the positive and the negative charge will attract each other and the robot will go zoom and it'll collide. So what we do is we place in high negative charges at the periphery of all obstacles. So what the robot does is the robot feels an attraction towards the goal. This is what it is. It's attraction towards the goal. The robot feels a repulsion from one because of the negative charges here. This is negative charge, this is negative charge. So it feels a negative force over here. The robot also feels a repulsion because of this obstacle. So that's the repulsion because of this obstacle. Now, what you see is different is the fact that if the obstacle is far away, it doesn't cause any repulsion. If the obstacle is reasonably far away, it causes some repulsion. So far away that it did not even affect this robot. And this obstacle was reasonably far away, and therefore you see the repulsion is extremely small. The boundary will also repel. The boundary is close by, so the repulsion is very large. And this obstacle is reasonably far away, so the repulsion is very short. So add up all the forces, repulsion due to this obstacle, repulsion due to the boundary, repulsion due to this obstacle, and a repulsion due to this obstacle, and the attraction towards the goal. This is your total force. That's where the robot will go, and that's how the trajectory would be. When it starts coming near this table, it will start repelling, and it'll start going here, and then once it goes away from this, the repulsion will ease out. The more away you go, repulsion stops, and then it'll feel strong attraction, strong attraction, strong attraction. It'll come all away around over here. That's what's the potential field. It's of course made from the potential function, which is minima at the goal, and it reduces drastically at the goal. So thing is that when it reaches the goal, the potential or the force becomes 0, so that you also stop at the goal. You just don't go in any direction. So imagine this figure around the goal here. This is where the figure is. And imagine this beautiful 3D space, which is this figure saying that the rainwater will come here, where the rainwater is the robot, and the rainwater will be guided by the slope all the way over here, which is our goal. So the rainwater is the robot, and it will get guided all the way up over here. So it's also called, it's similar to the rainwater algorithm, and the rainwater feels this force at every point of time. Away from the goal, you feel a strong urge to go towards the goal. Near the goal, you don't feel that much of urge. It's almost 0. The other thing is that you should never collide with an obstacle. So obstacle try to shoo away the rainwater. So the rainwater, it tries to go all the way up to the goal, but there are buildings and the rainwater cannot go on top of the building. So the buildings shoo away the rainwater. That's what it's doing. In normal areas, the buildings don't contribute anything. It's zero. Far away from the obstacles, the rainwater is not affected by building. It's just flat. Buildings say, do whatever you want. We don't care. But near, the buildings try to quickly get the rainwater down. So all of them try to quickly get the rainwater down in any direction possible. That's what you see around over here. The buildings these are the buildings 1, 2, 3, 4, the 4 obstacles, and they're shooing away the obstacle. They're saying, no, go here, go here, go here, go here, go here. They're trying to shoo away. The shooing away is larger near the building, and the go away is constant or zero or almost zero far away. So just imagine how beautiful the algorithm is, nature inspired. I wanted the robot to go at the goal, so I let the entire workspace have a slope leading towards the goal, and then the obstacles were the buildings that try to say, go away, and the rainwater obviously goes in and falls deep into the buildings. I just add the two forces up. So if I cut out this segment, because these 4 buildings are very large, you see buildings are showing away over here. And the natural slope is here. So if any water falls anywhere, it goes all the way up to the goal. It goes all the way up to the goal. Such a beautiful algorithm. The only problem is that, of course, if it would have been the best, I would have only talked about that. When it rained last time, the water didn't go to the rivers. Nature has designed our world also in such a way. Water goes from the Himalayas obstacle all the way up to the oceans. That's not what happens. So last time it rained from whichever city you are, what actually happened that there was water logging. There was a water which was at the local minima. In order to go anywhere, it needs to take a jump. This algorithm cannot take a jump. And that's exactly what happened. So let me show you where the local minima is. Over here, I am right at the boundary. The boundary shoo me away, go away, go away. I come over here. And now this obstacle shows me towards the boundary. I go towards the boundary shows me towards the obstacle. So the building and the boundary wall are so close that I go near the building pushes me away. I go near the boundary pushes me away, and I am at a local minima. I'm this water log. If it actually rains, there will be water logging over here. And therefore, your robot doesn't reach the global minima, which is the goal. It goes only on the local minima, which is the water logging here. It's worse when there are concave obstacles like this. So there's too much of water logging, which is from our analogy, as you know, as the lakes, local minima, where water logging happens. So concave obstacles, they add up a lot, and hence, what I really need to do is, one way, get rid of the local minima, but then looking at the space and getting rid of the local minima is a computationally expensive algorithm. And I want a reactive behavior. I want a behavior which is extremely, extremely reactive. And because I have a behavior which is extremely, extremely reactive, therefore, I cannot invest time on analyzing the space. So that's one of the problems. The good thing is that, remember, my robot has, a lot of people ask me practically, how is potential field implemented? Beautiful story. So what do I need for a potential field? Number one, attraction towards the goal. I know my location always, localization. I know the goal location always, HCI. So somebody tells me the coordinates of the goals. That's human-computer interaction problem or the human-robot interaction problem. Then my laser strikes an obstacle and reports me distance to the obstacle. Every laser strikes at an angle. So in order to calculate repulsion force, what do I need? The inverse square giving me the magnitude, distance gives me the laser gives me the distance, and the direction of the force, it's opposite to the direction of the laser. So if laser striking at 30 degree gives me 1 meter distance, I say force is equal to k1 times 1 upon 1 square times cos theta 30 sine theta 30. So cos 30 sine 30. So it's a very practical algorithm, easy to implement. The only problem is that it gets into local minima absolutely very easily. Now, let me first go on this thing. So technically, potential field has been since 70s and 80s. It was one of the first motion planning algorithm by Osama Khatib, of course. Extremely old man now. It's weird to see the pioneers of robotics are now terribly old. So it said two things: attraction towards the goal and repulsion from the obstacles. And the free body diagram, attraction towards the goal and repulsion from the obstacles is what drives the robot. Much recently, when people started operating into the robotic space, something changed. So when I would go towards the robot would see me as an obstacle, and our story would be robot avoiding me. While what really happens, I've got another faculty colleague just after this wall. When I see him and he sees me, we don't treat each other like enemies. You stay away from me. You stay away from me. How dare you come near me? And like enemies, we are very far off. We leave what's called as a comfortable distance, neither too close nor too far. If me and my faculty colleague, while walking towards each other, are too close, our wives will not like it. What's going on? I'll tell the director to change your place immediately. That's too close. That's intimacy. And if we are too far off, all our PhD students would be thinking they are not on talking terms. There's a problem. So if I go from here and my faculty colleague goes from here, we leave a comfortable distance. We don't go too far, that's rude. We don't go too close, that's intimate. We just leave enough distance. So it's modeled by two ways. One is you say that attraction towards the goal as it is, repulsion from the obstacles as it is, but the third factor, for people, too far away, attraction, too close, repulsion. So people are weird social beings. Far away, we attract, too close, we repel each other. So like we've got the lockdown and all our college couples are away, there's a severe attraction going on that we can sometimes observe. When they are too close, we hear in cases of fights, too close for intimacy leading to problems. So that's what we want to leave between people. Now, one way is to, of course, say that there'll be attraction, there'll be repulsion, both between people, and there'll be a natural equilibria. You can say attraction is equal to repulsion and get the equilibria. The third way is there's one equipment that naturally has that. It's called as a natural spring. Too close, it repels, it pushes. Too far, it attracts. Natural spring. So that's one of the modern things in the motion planning world, to model a spring force between every two humans, attraction and repulsion. Okay, and there's another thing which is weird with humans. So if you're walking like this and somebody is here, you are very cautious. So you stop at a comfortable distance. That's a comfortable distance. But if somebody is at the side, that's a comfortable distance. If you want to visualize it, you're driving on a beautiful highway in a monsoon weather, there is a vehicle in front of you. You leave a comfortable distance, which is usually a couple of meters. It's by standards, by the way. The distance that you leave is extremely risky. You have to, by law, keep enough distance such that if the person in front, for any reason, heart attack, whatever, applies a power brake, immediately you have enough time to stop. I ask a lot of drivers, why don't they follow the rule? They say, Saab, you don't know. The other vehicle will come in front of me, and then I'll have to maintain 2 meters from him. Then another vehicle will come. Don't teach me traffic rules. So from the vehicle in front, you leave enough distance. From the vehicle at side, you don't leave that much of a distance because the risk is much less. You'll have only a small lateral drift, but you can have a lot of large longitudinal uncertainties. And therefore, we say that the forces also taking direction into account, the repulsion is very high in the direction of motion and the repulsion is zero away from it. Anyone behind you don't care. And it takes on this nice elliptical shape. Side, it's the lowest. So least behind, highest ahead, and side next lowest. And it keeps on increasing as you go in the direction of motion like this in an elliptical manner. So I talked about social forces where people attract and repel, and I gave it directionality. These are the modern things which are going on. That's what's called as the elastic strip. So I said probabilistic roadmap have a problem. They don't take into account when people move. That's what you do. You have a source, you have a goal computed by probabilistic roadmap. When people move, the elastic strip deforms. So that's a rubber band, by the way. As people move, they exert force, and that force changes how this thing should be. So a person wanted to go from here to here. As this person started walking in, the person kept on having a deviated path. That's what is elastic strip. And this is the last topic that I'll formally cover in a bit of a detail. So that's my last topic for the day. It's called as a fusion of a deliberative and a reactive planning technique. So let's study two algorithms as we saw it, one deliberative, one reactive, potential field and, probabilistic roadmap, deliberative, and potential field, reactive. And let's try to see, are there limitations of both of them? Probabilistic roadmap cannot handle dynamic obstacles. Elastic strip is a cheat. It has other troubles. Like what if going from behind was the actual thing? So probabilistic roadmap, fab algorithm, brilliant, works up to 24-dimensional spaces, collision-free paths, beautiful paths for the robot. It cannot handle one thing, dynamic obstacles, suddenly appearing obstacles. It works on static only. Potential field, amazing, beautiful algorithm, rainfall and attraction and repulsion, beautiful. However, it cannot handle one thing, which is overcoming local minima, and practically every environment will have a local minima. So we've got a weird situation. Neither probabilistic roadmap works for in real life. I can send my robot to my PhD scholar using probabilistic roadmap. Somebody moves, my robot says, I give up. And then it waits for 5 seconds for things to settle down and then makes a move again. Or potential field where I send it to my research scholar, it gets trapped in the local minima and it's there forever. So somebody has to call me up, so it's stuck. And then you shape the obstacles in such a way it gets out, it gets into another local minima. So what we do, we fuse the two up. Now, The reactive algorithm is, as we call, as more local in nature. It can only do local small decision makings, avoid one obstacle or maximum two, just get some immediate motion, react to nearby obstacles. It's a very local algorithm. Deliberative planning is a very global algorithm. It handles things like, is my path optimal? Is my path valid? It's a sound, all those formal properties. It's a very global algorithm. And the fusion will be very similar to the ones in evolutionary computing. Will know it by mimetic computing, global plus local. The ones into traditional AI will also know it as a fusion of global plus local. The ones into, so optimization, you talk about global algorithms, genetic, you talk about particle swarm, you talk about local algorithms, simulated annealing, hill climbing, gradient descent. And it's a fusion between the two that does the thing. That's exactly what I'll do. Now, my potential field is the actual algorithm that I'll use. That's my base algorithm. The problem with potential field is that it can only overcome one obstacle like this. It cannot overcome more than that. So what do? I say that my potential field algorithm will not try to go to the goal. I repeat, my potential field algorithm will not try to go to the goal. My potential field algorithm will try to go to a subgoal. And if you have kids, same problem. If you tell your kids when they are born, you have to clear IITG, it's too far, it doesn't work. So you tell them, okay, you study today, I'll give you chocolate, sub-goal, you study and pass this exam, I'll give you, okay, I shouldn't be giving examples of bribery, not as a government officer. So anything which is hard, you break it down into sub-problem. IPL, you say 20 overs, I cannot plan. So you say that, okay, let's plan 5 overs. This is my approximate target, and then I'll do. So you don't plan a sub-goal, you plan a sub-goal, where sub-goal is the last point visible as per the current robot position. And the robot tries to just get to the sub-goal. See, there's no obstacle. When it's here, it only gets a sub-goal. Now, potential field can easily attain the sub-goal. When it's here, it gets the sub-goal, which is also the actual goal. So the fusion algorithm works in 3 steps. Number 1, plan a deliberative trajectory, probabilistic roadmap, and get a deliberative trajectory, probabilistic roadmap. Very easy. Number 2, what happens is once you get a trajectory, probabilistic roadmap, goal is too far off. Goal is too far off, give a sub-goal. Take a sub-goal at a short distance or as the last point visible. So for this is the sub-goal, for this is a sub-goal. So take a sub-goal. As a robot moves, update your sub-goal. So robot is coming near the sub-goal is also moving. That's what you do with kids. Okay, get very good marks in 10th, then get very good marks in 12th, then get very good marks in first year engineering, get very good marks in final year engineering, get very good placement, marry, have kids. Sub-goals. The moment somebody is about to reach a sub-goal, you change the sub-goal to something more difficult. Reach that sub-goal, you change it further apart. So you plan a deliberative trajectory, you get a sub-goal, you move the sub-goal as the robot comes near the sub-goal, and the robot is nothing but a potential field algorithm, simple, that's trying to get a sub-goal, simple. If a dynamic obstacle comes, potential field algorithm will be able to handle it. It's that capable. If a very complicated algorithm comes or like the complete map changes and stuff like that, that of course cannot be handled. And using this is practically how every robot that you see in movies, the robots that you see in science fairs, the robots that you see in your college, they work. A fusion of a deliberative algorithm handling the static map and a reactive algorithm, which is handling the dynamic part of the map. I do have some videos which I sometimes play, but then this is only when I have kids. I think I'm too short of time. So the map was made by a deliberative robot, and this robot is only doing reactive. That's a fusion between deliberative and reactive. So this was a new obstacle. The reactive algorithm avoided it, not the deliberative one. And this is the actual robot that you see working. So that's again a fusion of deliberative and reactive algorithm, which is working. I'll get you this thing. Here, what actually happens is that there's a hole. You should be able to see it, and the robot thinks it will get drowned into the hole. So the reactive algorithm says, no, there's a hole. Don't take that risk. So it's a fusion of deliberative and reactive, and it's achieving a series of goals. This was a robot. You would have seen this one many times. So sometimes what we do is that we place overhead camera, and the green one is our localization system, color filtering, and the thesis are the obstacle. I plan and move a robot completely using the overhead camera. So there's no problem of localization or mapping per se, and that's just a robot following. I think I'll come on. If you want a quick simulation tool, then use VREP. It works on Windows, and it's the easiest simulation library that you can get. It also uses the RRT algorithm, and it is also open source. So normally I tell people to start off with VREP, and after they have done the VREP thing, then move into ROS, and then move into OMPL, and move it and Gazebo as the libraries. And that's all from the presentation.
Thank you so much, sir, for such a wonderful session. And I hope all the participants are getting the word of wisdom from you and they're getting very nice session. Now, I would like to call Mr. Yogesh, sir, for the vote of thanks.
Thank you, ma'am. The second session was delivered by the Dr. Rahul Kala, Assistant Professor in IIIT Allahabad. Topic was robot motion planning. He explained the following topics: understanding SLAM, probabilistic roadmap, configuration space, uniform sampling, Gaussian sampling, RRT, MPL, reactive planning, and artificial potential field, social potential field, elastic strips, and last one is the fusion. Now, thanks to Dr. Rahul Kala and all the participants to listen carefully. Thank you. Thank you very much.
Thank you so much, people. Wonderful having spent time with you.
Thank you so much, Yogesh, sir, and thank you so much, Dr. Kala, for joining with us. Thank you so much. So now